Okay, let's just review what we discussed. So Newton's law of motion F equals ma. What it really means is the sum of the external forces equals ma. We learned these friction rules last time, right? And equilibrium, sum of the forces equals 0. Non-equilibrium, sum of the forces equals ma. And you split them up into x components and the y components. That's really all. Okay. Oh yeah. So the next two questions are really important. That's all I can say. You might see them again. The picture below shows a person exerting a constant horizontal force F on a box. Thus, the box moves along the floor with a constant horizontal velocity v. The magnitude of the force that the person exerts on the box, blah, blah, blah. All right, so pause your video and figure it out. Okay, we're back. Again, if it were me, when I'm reading this problem, as soon as I see this word constant velocity, I circle it or underline it or something like that. Because if the velocity is constant, it means the acceleration is 0. It means that the sum of the forces is 0. Right? So it's an equilibrium problem. So what does that mean? The magnitude of the force that the person exerts on the box has to be equal to the frictional force, right? Because, I mean, if you're going to draw the force diagram, you know, you have F this way, you have friction that way, but again, the horizontal velocity is constant, so the acceleration is 0, so this force has to be equal opposite to that force, right? Because we're going to say that the sum of the x forces equals F minus F, which is friction, okay? And that has to be 0, right? Because acceleration is 0. So, I don't know, I think it's really worthwhile when you get questions like this, just draw the force diagram. It just will help you. Okay, so again, the box moves with a constant horizontal velocity. Acceleration is 0. So the force that this person is exerting on the box equals the frictional force. Okay, now let's do something similar. Referring to the previous question, if this, and by the way, what kind of friction is this? It shouldn't have been so sloppy. This is kinetic friction, right? Because the box is moving. Kinetic friction. And don't forget, kinetic friction equals mu k n. But what's the normal here? Well, you know, it can be n mg, right? And the thing is not accelerating this way, so the normal is just mg, so it's mu k mg, right? So it's constant. That doesn't change, you know. Okay, equals constant for this problem. Right? Because mu k depends on the surfaces, the mass is the mass, and g is g, you know. Okay. All right. Referring to the previous question, if the same person now exerts a horizontal force 1.001 F, just a little bit more than before, on the same box, across the same floor, why did they say that? Because mu k is going to be the same. Then the box moves what? Okay, so pause your video and figure it out, please. Okay. In the previous question, we said that F, the force that the person exerts on the box, was equal to Fk, right? Which is mu k mg. But now, what we have is 1.001 F. Well, therefore, this is slightly larger than that. Agree? It's slightly larger. So this is going to be bigger than that. So it's not equilibrium anymore, right? It's going to accelerate, right? It's going to accelerate. And so what's the answer? 2. Acceleration means that the speed is going to continue to increase, right? So the box moves with a continually increasing speed. I mean, it's going to increase slowly, most likely, but I don't care. The point is, On the first one, right, on the first one, we had A equals 0. On this one, we have A not equal to 0, right? A is going to be positive. So A is going to be in this direction, velocity is in that direction, the speed is going to be increasing continually. Make sure you understand this, that one, and that one, because you will see these again. And this is really the crux of Newton's second law of motion, right? So make sure you understand these two questions. All right, we've talked about free fall in the past. We're going to talk about it a little bit more now. So here's an example of free fall. So I have this object. I think I can. It's a good idea, or it's proper to ignore air resistance. So when I drop it, the acceleration in the y direction equals minus g, right? A sub y equals minus g. Okay? So it's free fall, you know? The only force that we care about is the force of gravity. We're ignoring air resistance. Oh, I forgot to bring a tennis ball. Ah, gee. Well, what can I wreck? Hope I don't wreck anything. Okay, just pretend it's a tennis ball. It doesn't really matter. It can be anything. All right? Well, actually, I'm just going to fake it. All right? I'm just going to show you the picture. Okay, so just pretend I have a tennis ball, and I just barely throw it. So I throw it horizontally, but not with a lot of force, you know? So it just kind of goes down pretty soon, right? So that's supposed to be the picture where you're throwing it with not much force. Of course, this is completely ridiculous, right? I mean, this is pretty far, right? But we don't care. All right? So I throw it, not a lot of force, horizontally, it just goes down. All right? Now, again, come on. Once the ball leaves your hand, or my hand, sorry, what's the only force acting on it? Gravity. So it's free fall. Agree? It's free fall, you know? Okay. All right. Now I'm going to take that same ball and I'm going to throw it harder. You know, throw it a little harder. So now it's going to go, it's not going to just fall down quickly. It's going to fall down maybe over here or something like that. Okay, so that's supposed to be this. Pretty far, right? All right? Okay. And again, once the ball leaves my hand, the only force acting on it is gravity. We're ignoring air resistance, so it's free fall. All right. Now, you know, I'm getting psyched. I had my Wheaties for breakfast. I'm going to take that ball and I'm going to throw it so fast. Oh, hit the microphone off. That's what I'm going to do. So I'm going to shoot that ball so fast that it's going to go all the way around the Earth. Okay? It's going to go all the way around the Earth, and it's going to hit me in the back of my head. Right? Got it? So I'm going to throw it so hard, it goes all the way around the Earth, hits me in the back of the head. Now, hey, this is just like the other ones, except that I threw it with a greater force, you know, so it had a larger speed. But still, you know, once the ball left my hand, the only force acting on it is gravity, so it's free fall, right? It's free fall. So all of these, you know, all of these are free fall. That's free fall, that's free fall, and when it hits me in the back of the head, it's free fall, you know, it's all free fall. Okay, so, wow, what have we just figured out? So, you know, this is free fall, right? But also, when I take a ball and I throw it, and orbits the Earth and hits me in the back of the head, that's free fall. They're both free fall. So falling balls and orbiting balls are both examples of free fall. Okay? Now free fall, that means the force of gravity is the only force acting on it. That's important. So that means that falling balls and orbiting balls both obey the same law of gravity. Right? Now, forget about having a ball here. How about a satellite? If you have a satellite that orbits the Earth, what kind of motion is that? It's free fall, right? So again, a falling marker and an orbiting satellite, that's free fall. And they both obey the same law of gravity. Okay? So what we're saying is that, well here, let me show you a picture. Okay, so really, you know, when we talk about the moon orbiting the Earth, well, the moon is actually falling toward Earth, right? Come on, isn't this falling toward Earth? That's free fall, agree? Well, isn't the orbiting moon falling toward Earth? What? Well, let's see. Okay, so let's suppose, so here's Earth, there's moon. So let's suppose, right at this moment, remember, the velocity of the moon is perpendicular to the radius. We talked about that in gory detail before, right? So the velocity of the moon is this way, right? Okay, so let's say that, you know, the moon is orbiting the Earth, right? And then let's say it gets to this point, and for some reason the gravitational force quits, just ceases to exist. Well, what would be the direction of the moon? It would go this way, right? Just keep going this way, you know? But if there is gravity, the moon follows a circular orbit, right? It goes this way. So, without gravity, it would be here. With gravity, it's there. So is the moon falling toward the Earth? Yes! Well, why doesn't it hit the Earth? Because it has the right speed, right? It has the right speed. I mean, look. This one hit the Earth because it was going too slowly. This one hit the Earth because it was going too slowly. This one did not hit the Earth because it had the right speed. Okay? So what I'm saying is that when the moon orbits the Earth, by golly, it is falling toward Earth. But it doesn't hit the Earth because it has the same speed, the correct speed. Okay? Correct speed. So now you should say, okay, what's the speed? Well, we can actually figure it out. We know enough now to be able to figure out the correct speed so the moon doesn't smash into the Earth. Okay, so let's forget about the moon for a minute. Let's just say we have a ball. So we're going to say that the ball is really, really close to the Earth. And we want to know how fast that ball is moving in order to orbit the Earth and smack me in the back of the head. Okay? All right, so here we go. So we have, this is circular motion, right? This is uniform circular motion. Okay? So the sum of the radial forces equals ma radial. That's r, sorry. Okay, and what's a radial? V squared over r. So we have mv squared over r. Okay, well, if it's close to the Earth, what is the only radial force, or what's the only force for that matter? What's the only force acting on it? Gravity. If it's close to the Earth, what's the gravitational force? The weight, right? Just the weight. So that's just mg, you know, right? Sum of the radial force equals ma. It's Newton's second law. A sub r is v squared over r. So we have mv squared over r. The only radial force is gravity, so it's just mg. So if you look at this, okay, just look at that. We're going to get the velocity. So look what cancels. The mass cancels. And we want to get velocity multiplied by r. And we want to get velocity of square root. Bingo. All right. So there it is. Okay. So that means if we had a perfectly spherical Earth, you know, no trees, mountains, and all that stuff, right? And if you stood on a chair or something like that, and you threw a ball at this speed, it would literally orbit the Earth and smack you in the back of the head. And notice it doesn't depend on mass. So again, this is no air resistance, right? So this would work with a baseball, a ping pong ball, without air resistance, you know, a car, anything. They'd all have the same speed, right, in order to orbit the Earth. Okay, so now you say, well, okay, that's fine. How about let's do something that's not close to the Earth, like the moon, you know, or orbiting the sun or something like that. Okay? Well, now we've got to use Newton's law of gravity. All right, fine. So the sum of the radial forces equals ma sub r. Again, yeah, let's do the Earth orbiting the sun. All right? That's kind of a good example. All right, so this is the Earth, right? So we have m Earth v Earth squared over R. Okay? So uniform circular motion, sum of the force equals ma, but A is v squared over R. Okay, but now, again, it's weight, right? I mean, here's the sun. Here's the Earth, right? So the Earth is orbiting the sun. So it's free fall. The only force is gravity. But now it's far away from the sun, so we're going to use Newton's law of gravity. So it's G, remember that constant, M sum M Earth over the distance squared. Right? So I'm saying this is. So R is the distance from the center of the Earth to the center of the sun. Okay? Alright, we're trying to get to the velocity of the Earth again, so get rid of all that stuff. So notice what cancels. Mass of the Earth. Okay? Multiply both sides by R, so that goes away. That goes away. Take the square root. Bingo. There you go. Alright. So that is the velocity of the Earth. It's that gravitational constant times the mass of the sun divided by the distance between the center of the sun and center of the Earth. Square root of. There you go. Pretty cool. And again, it doesn't depend on the mass of the Earth. Right? It doesn't depend on the mass of the Earth. Okay, think of the following. Let's say you go up to the EA point and you jump off the cliff. How do you feel besides scared? How do you feel? I mean, you don't feel anything, you're not touching the floor, right? So, you feel weightless, right? Because you're not pushing down on some solid object like the floor, okay? And the floor's not pushing up on you. So you feel weightless. However, I mean, are you weightless? No. The force of gravity is pulling down on you, right? But you feel weightless. You jump off the cliff, you feel weightless. Now let's say you go into orbit around the Earth, like an astronaut or something like that. No. Okay? Again, when you're orbiting the Earth, that's free fall, right? We just discussed that. That's free fall. So how do you feel? Well, let me back up. Well, I already said it. When you jump off the cliff, you feel weightless. When you orbit the Earth, you feel weightless. Because there are both examples of free fall. When you jump off the EA point, ignoring air resistance, that's free fall. When you orbit the Earth, that's free fall. So you feel weightless in both situations. Are you weightless? Are these guys weightless? My gosh, no. I mean, come on. Here's the Earth, right? I mean, they're circling the Earth, right? And so the force of gravity is making them circle the Earth. So they are not weightless, but they feel weightless. Just like you feel weightless when you jump off the EA point. Right? Gravity is pulling them towards the center of the Earth. Like gravity is pulling on you when you jump off the EA point. Okay? If you didn't have gravity, what would you do? What would these guys do if all of a sudden gravity quit? They would just go in a straight line somewhere. Okay? So, people astronauts who undergo this weightlessness, they have to get used to it. Feeling weightless is not easy. So they have a training jet to help them get used to this. And we're going to learn later on, if we haven't learned it already, that when you undergo parabolic motion, that's free fall, what we call projectile motion. And so what they do is they put these poor people in this jet, and they make them undergo this parabolic motion. Now you can imagine, people have been on an airplane. How does it feel when you're flying horizontally and all of a sudden you go make a little dip? Oh my gosh, right? So how do you think these people feel? That's a huge dip, right? So what do you think people do when they're in this plane? Well, they vomit, right? And so this plane is called the Vomit Comet. Pretty cool, huh? All right, but again, it's a nice parabola, free fall, projectile motion. Okay? So all I'm saying is that jumping off the cliff and orbiting the Earth is exactly the same motion. It's free fall. Simple as that. All right, so here's a cool quote, which you probably have to read 3 times to understand it, which is true for everybody, so don't feel bad. One has to be a Newton, Isaac Newton, to see that the moon is falling when everyone sees that it doesn't fall. What? So this goes back to this slide. All right, the moon is falling, correct? It is falling toward Earth, but it orbits Earth because it has the right speed. Right? So somebody had to be a genius like Newton to figure out that the moon is falling, when to us it doesn't appear to be falling. Because, you know, when we think of something falling, we think of something like this, right? Okay, so what did we learn? Orbital motion is the same as dropping something. Both examples of free fall. Okay, now new topic. Now we're going to talk about drag. Finally, we're going to talk about air resistance. So we're going to talk about, so drag is the word for the air resistance force, the drag force. And so we're going to talk about drag and something called terminal speed. Okay, so consider raindrops. Do you think free fall is a good model for raindrops? I would say no. Why? Because air resistance is important. You know, I mean, you know, they fall quite a distance, so you know you can't just ignore air resistance. Okay, so there's drag. That's important. How about dropping a penny from the top of the Empire State Building in New York City? Is that free fall? Again, probably not. You know, it's a long distance, and so air resistance or drag is important. Now, I looked this up on the web. I don't know if it's true. I shouldn't be so lazy. I should figure it out for myself, but I haven't yet. Sorry. Okay, so this is what happens if you drop a penny from the Empire State Building, according to this website, which I don't know is true. All right, so they claim with air, it would be going at 25 miles per hour at the bottom, at the sidewalk, which is supposedly painless. I don't know about that. And they also claim without air, so this is with drag, right? It slows down, you know, I mean, you know, well, it's only going 25 miles an hour at the bottom. Without air, so free fall, in other words, no drag, it goes 210 miles per hour, which would certainly break your skin. So this is just, I mean, I don't know if these things are true, but it just shows you that air resistance is really important, right? I mean, 225 compared to 210. That's huge, right? Okay, so I'm just going to show you a simple model of air resistance. It doesn't work for all things, but it works for like runners and cyclists and things like that. Okay, so it's kind of nice. So this is an equation for the drag force. Again, the air resistance force. Okay, the drag force. All right, so. Okay, so 1/2 goes C. It's called the drag coefficient. You know, C coefficient, right? So C is a drag coefficient. So if it's a falling sphere, C is about 1/2. If it's a cylinder falling down, end down, it's about 0.8. If it's a cylinder falling side down, it's like 1.1. So I mean, C, you look it up, you know? You look up what the drag coefficient is, that's C, okay? Rho, we always, in physics, we usually use rho for density. Now, so what kind of density do you suppose we're talking about? The air density, okay? So rho is the density of air, all right? And you can look that up. Okay, A is the cross-sectional area of the object. So for example, let's say you're a cyclist and you know, you're going this way and there's a horrible wind coming at you. If you want to decrease the air resistance, what do? You do that, right? No. You know, you get like this, right? You're trying to reduce your cross-sectional area. And the V is the velocity of the object relative to the air. I really wish Randy Knight, when he included this equation in his book, I really wish he would have said V relative. Because it's confusing. I mean, how would you know, you know? You might think it's the velocity of the object relative to the ground or something like that. It's not. It's the velocity of the object relative to the air. And that's super crucial, all right? So remember that. V is the velocity of the object relative to the air. Okay? Now, what's the direction of the drag force? Well, obviously opposite to the direction of the motion, right? If something's falling this way, the drag is this way. If I shoot something this way, the drag is that way. So the drag always opposes the motion, right? Okay, let's get back to the rain, you know. Look at that equation. Basically, what it says that the drag is proportional to the velocity squared, right? The velocity squared, okay? So I think of, think of a raindrop. I mean, gravity is pulling it down. Drag is going this way, gravity is going that way. But I mean, it's going to be going pretty fast, right? But what it means, though, the drag is going to increase really, really, really rapidly because it's proportional to the velocity squared, right? So, you have this raindrop at rest. It starts going faster and faster and faster. But then the drag starts getting bigger, 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 big time. Now, look at it. Eventually, what's going to happen? Eventually, the force of gravity is going to be equal to the drag force, right? So this is what we would do. Our little force diagram. Here's the force of gravity, the weight, and here's the drag, right? So eventually, what I'm saying is eventually the drag is going to equal the weight. Now, what happens then? You know enough now to answer this question. When the drag equals the weight, what's the net force? 0. Therefore, what's the acceleration? 0. Therefore, the raindrop stops moving, right? Wrong! Right? It just keeps going at the same speed, right? Same speed, okay? So when this happens, when the drag equals the weight, the acceleration is equal to 0, and the velocity, we call it V terminal, right? The terminal speed, right? The terminal speed. And we're usually lazy, so we just call it VT, okay? And in other words, when the drag equals the weight, it's just going to keep going at that same speed, the terminal speed, okay? And for rain, VT is about 5 meters per second. It's not important to know that, it's kind of interesting, okay? Let's figure out an equation for the terminal velocity, okay? Let's do that. All right, so the drag is 1/2 C rho A B squared. And we want to put that equal to, so the drag equals the weight, mg. Now we want to solve for V. So we multiply both sides by 2 and divide by C rho A. C rho A. And take a square root. All right, so that's an equation for the terminal speed, or the terminal velocity, right? When the drag equals the weight. Now notice, notice we have a mass here, right? And so if it's a massive object, the terminal speed is going to be big. If it's really light, low mass, the terminal speed is not going to be so big, right? Okay, who knows what a hailstorm is? Right, so like Colorado, they have these things. I was in Colorado once. I don't remember the place, the city, but anyway, I was in Colorado once. It was late spring, early summer, or something like that. Nice day. Then it got really dark and cloudy. Then it started to rain. Then it started getting colder. And all of a sudden, the rain turned into a hailstorm. So basically, you have these little spheres of frozen water, ice. That's called a hail. H-A-I-L, hail. So you have these little hailstones hitting the earth. And at some places, the hailstones just small. Some places they can get big. And so think about it. If you have a really big hailstone, like the size of a softball, has a lot of mass, so the terminal speed is going to be really, really big. Well, and so it can do a lot of damage. So let's see if I have a slide. Okay, I don't want to go there. But anyway, so you should look at this website. You should go to this link. So they had this hailstorm in Colorado in April 7th, 2018, and they had these big hailstones, and they were smashing, people's cars and breaking windshields and all sorts of crazy things. So again, just because of this, right? The bigger the mass, the bigger the velocity. So it's going to be enough energy to break the windshields. Okay, keep talking about this drag. All right. In 2011, there was a guy, Jeffrey Mutai from Kenya. He ran the fastest marathon to date. Right? This is 2011, a little old, right? So he did it in 2:03:02. That's 26.2 miles, just a bit over 2 hours. It's amazing, all right? But he did this at the Boston Marathon. So you start here and you end there, right? So again, to that point, that was the fastest marathon ever. But it was not accepted as a world record. Why wasn't it accepted as a world record? What do you think? Well, what if the wind is pointing this way the whole time? Would that be fair? Of course not. So they never allow world records to be set. This is called at a race, which is basically in one direction, Okay? It's called a point to point, right? Because it's just not fair, because you could have wind pushing you along. So it was the fastest marathon, but it was not counted as a world record. So that's Boston. Now here's the Berlin Marathon. Where's the start? I don't know. I guess it's here. Yeah. So here's the start, and then they go all these crazy loops. So if you run a really good time in Berlin, is that going to count as a world record? Yeah, because you have all these loops, right? And so the effects of the wind are basically canceled out. Okay, let's quit.